Welcome everybody. I want to introduce today's speaker, Gottlieb, who will tell us about tomorrow's frontiers and today's discoveries in multi-messenger astrophysics. Is here partially because he attended our conference on multi-messenger and computational astrophysics for the previous 3 days, but also he kindly agreed to give one more talk, which is an effort, I guess, but thank you so much for being here and giving an extra talk also for the employees of the Institute of Physics. Ore graduated from Tel Aviv University. He did 2 degrees in computer science and in physics, 2021. And then he was awarded several fellowships, very prestigious ones. First one was the Rothschild Fellowship in Israel, as I know. Then the Sierra Fellowship at Northwestern University, and then at Columbia University. Currently, he's a fellow of the Flatiron Institute in New York. But what I also want to say, he just accepted an offer for the permanent position and professorship at MIT. So welcome you very warmly, and I hope we will hear now a lot of excellent news about multi-messenger astrophysics in general. And please start.
Thank you, Agnieszka. Thank you all for coming. I'm still not exactly sure what the different backgrounds that everyone has. So please feel free to stop me if anything I'm saying doesn't make sense or not clear. So we are going to talk about one of the most cutting-edge topics in modern physics, which is multi-messenger astrophysics. And we will start with the event that has started the field of multi-messenger astrophysics in the past few years, one of the most important astrophysical events in the history. And we will see the new opportunities that it unlocked, and what all the physics that we could have studied through this event. And then we will see what the open questions that are still remaining, and talk briefly about what is expected for us in the near future of multi-messenger astrophysics. So as we are going to address several fundamental physics questions and deep astrophysical mysteries, let me start with the first question that we will get to talk about in this talk, and these are about the most luminous events in the universe. So the question of what are the most luminous events in the universe has been long established. For decades. We know that these are bursts of gamma rays. These are the most luminous events since the Big Bang, and we can ask about this question from 2 different perspectives. Observationally, when we think about this, we can ask, what do we actually see? And what we see are gamma ray bursts, in short GRBs. And these bursts of gamma rays are associated with 2 classes of systems, which are very different from each other. We can find them in 2 different astrophysical systems. The first are the relatively longer bursts. They can last for a few dozens of seconds, and they are associated with the collapse of massive stars, which leads to an explosion, what we see as a supernova. And these supernovae are normally associated, specific classes of supernovae that is associated with this long gamma ray burst. And this scenario has been suggested by Stan Woosley over 3 decades ago. The other type of gamma ray bursts are the shorter gamma ray bursts. And these ones, they last for a fraction of a second. And we normally see them, and we will talk about this more, when we have 2 compact objects, can be a neutron star and a black hole, or 2 neutron stars that are merging. And after the merger, there will be this flash of gamma rays, which is also very, very powerful. And these are known to be short gamma ray bursts. And originally, or the first one to propose the idea that they are coming from mergers of compact objects is Paczynski in 1986. So this is as far as we can talk about observations, but we can also ask from a theoretical perspective, if we are interested in the brightest events in the universe, what is the energy source, right? This is one of the most interesting questions to ask. Where do we bring all this energy from? Now, the theoretical question is actually a little bit harder, and the reason is that we know that these gamma rays, they come from very, very fast outflows that are moving with Lorentz factor of at least a few tenths, maybe even more. So they are practically moving at the speed of light, and this implies that they must come from collimated outflows known as jets. But the jets are generating the gamma rays, but if we're interested in the energy source, what is powering the jet then? And the reason why this question is so hard to answer is because as far as the jet is concerned, whether the jet was powered by a black hole or a neutron star or some other object, there is no difference. So as far as the jet is concerned, we cannot distinguish between the different compact objects, and this is why the question of what is powering these jets in gamma ray bursts has remained an open question, at least in the context of short gamma ray bursts. So we will return to this question and try to answer it later in the talk, but before going there, let's talk a little bit, we will talk about how we can address such questions and maybe have a little bit background of what multi-messenger astrophysics is and why do we even care so much about it. So let's go and start from the beginning with multi-messenger transients and introduce them. So transients are events in the universe that are passing, they are not permanent, and this is why they're called transients. And multi-messengers means that we have at least two different types of messengers that are participating in these events. And let's introduce the four types of messengers that in principle we can have when we have transients. So the first is gravitational waves. And as you know, gravitational waves are basically perturbation in space-time when we have energy that has some acceleration. If we have a quadrupole moment in space-time, this will generate gravitational waves. So we just have, for example, an acceleration of mass, and this will lead to a wave that is propagating in space-time and is changing the curvature of space-time as it's moving, and this will emit the gravitational waves, and they can be detected here on Earth. And when we think about transient gravitational waves, there are two types of gravitational waves. The ones that are coming from inspiral sources, meaning they're coming from mergers of two compact objects, for example, neutron stars, and they will power gravitational waves that we can detect here on Earth. And there are the non-inspiral sources, which are sources that in principle emit gravitational waves, but we've never detected them. The reason why we haven't detected them, it's much harder to detect sources that are not coherent, and this is what we would expect from non-inspiral sources, and we'll get back to them later. For the moment, let's focus on the inspiral sources. So we have two compact objects, and as they are merging, they are changing the space-time around them, and this is what's emitting gravitational waves until they merge. As they fall into an inner orbit, gravitational wave frequency is increasing until the final merger. Now, if at least one of these objects is a neutron star, then, and that means that we don't have just two black holes, that means that we also have baryonic matter in the system. And if we have baryonic matter, it means that we can also have other types of signals or other messengers in the system. So, for example, if we have a neutron star, we expect two electromagnetic counterparts to the gravitational waves. So what would happen is that the neutron stars will merge, there will be some debris of neutron-rich ejecta that will undergo radioactive decay and power what we call a kilonova emission, and there will be a short GRB, which you just mentioned in the previous slide. So these are the two electromagnetic counterparts we expect in the case that at least one of them is a neutron star, at least one of the compact objects is a neutron star. And as you can see, both of them have been predicted by Fizyki already a while ago, and we had the first observational confirmation for both of them just recently, and we will get to this in just a minute. So far we introduced two messengers, gravitational waves and electromagnetic waves. What are the other two messengers that we can have? So if we have a jet and we have ejecta, the jet and the ejecta will interact with each other, and this will lead to the formation of shocks. So we expect shocks both in the jet and the ejecta. So for example, the jet is interacting with the ejecta, will lead to the formation of a shock. And this particularly will be a collisionless shock that is mediated by a plasma. And then we will have a charged particle that can cross the shock. And the charged particle will cross the shock and be scattered back and forth across the shock due to the turbulent magnetic field in the shock. And every time that it's crossing the shock, it will gain energy until it will become a very energetic particle. And this will be a high energy cosmic ray. And this is the third messenger. And then this cosmic ray can interact with the photon field in the jet and in the ejecta. And this interaction between the protons and the gamma, or the photons, will lead to the formation of pions that will ultimately decay to neutrinos. And these are the 4 types of messengers that we can have. So if we have 2 of these messengers, we have a multi-messenger transient. Where can we find these multi-messenger transients in the universe? There are, I would say, largely there are two sites where we can look into this, and not coincidentally, they're associated with black holes. And this is demonstrating the extreme physics that it takes to power each and every one of these messengers. So black holes can come in different sizes, but specifically we can divide it into 2 sizes, the biggest ones and the smallest ones. So the biggest ones are the supermassive black holes that can weigh millions or even billions of the mass of the sun, and they reside in the center of galaxies. And they can also be associated with multi-messenger transients, but I'm not going to touch on this class in this talk. And then there is the infant black holes. Their mass is just a few times the mass of our sun. They're a city-sized black hole, maybe roughly the size of Warsaw, just central of Warsaw probably. And they can be associated with several types of multi-messenger events. The first are binary black holes that are emitting gravitational waves, but if we have some baryonic matter in these systems, we will also have we will also have other messengers other than gravitational waves. Binary neutron star mergers, which we've just seen in the previous slide. Black hole neutron star mergers that will share very same physics, at least in some configurations, with binary neutron star mergers. Then we have the supernovae, which are known to be multi-messenger event. In fact, the first multi-messenger event that has been detected was in 1987, when we had neutrinos and light coming from a supernova. And then we have unknown cataclysmic events, which are new classes, new transients that are yet to be discovered or yet to be classified, that could in principle be multi-messenger sources. So this is the landscape of multi-messenger sources, but the question now is, why do we care so much? I'm talking about multi-messenger sources for 10 minutes already. Why does everyone care so much, and why are they so important? So I would like to demonstrate that point is showing you something that you might have seen before. The chain of events of the most important astrophysical event, I would say, in the past at least a few decades. This is a GW170817. It was a merger of 2 neutron stars 8 years ago, which sets the dawn of multi-messenger astrophysics. So we had 2 neutron stars. The neutron stars merged, and the total mass of the two neutron stars was about 2.7 solar mass, the mass of the sun. Now, for those of you who know, neutron stars cannot come at any mass, and there is a maximum mass that the neutron star can sustain before it collapses to a black hole. And this is roughly 2 solar mass. This is known as the TOV limit. So the question is, how these 2 neutron stars merge, and most likely led to the formation of a neutron star of a mass of 2.7 solar mass. The answer is that this neutron star was not really stable. It was supported by differential rotation, which is supporting it not just with differential rotation with centrifugal force, but also with some thermal energy that is coming from the shear between the different layers as it's differentially rotating. And this neutron star could have lasted for a fraction of a second before it finally collapsed to a black hole. So in this system of two neutron star mergers, of the neutron star merger that form a neutron star and later on a black hole, there were gravitational waves that were emitted, and this was the first time that we have detected gravitational waves coming from two neutron stars. Now, as you saw before, we expect electromagnetic counterparts, at least two of them, to follow after the gravitational wave emission. One is the kilonova, and one is the gamma ray burst. We have never seen kilonova and gamma ray bursts associated with neutron star mergers before, so this was our chance to finally confirm these predictions by Fizyki. So let's establish the different components here. The first one is the kilonova, which is this ejecta of neutron-rich gas that came from the merger. So there are two processes that can form this ejecta. The first one is the tidal forces that are operating between the neutron stars as they're coming together. There will be tidal disruption, and the disrupted neutron star will eject some neutron-rich gas. And then the neutron stars will actually collide with each other and expel even more material from the merger. Later on, there will be a formation of an accretion disk around the compact object, and the disk will also expel winds outwards, and this will be a further enhancement to the ejecta. So the ejecta was one of them, and the kilonova of the radioactive decay of the ejecta, and the other expected component will be the jet, which is emitted, which is powered by the compact object, whether it's a neutron star or a black hole, and this jet will power the gamma ray burst. Now, these two components, as you saw before when we demonstrated the shocks, are not independent of each other. There will be interaction between the jet and the ejecta. And this interaction will lead to a third component, which is what you see here as the jet is propagating through the ejecta. So this is the jet, this is the ejecta, and as the jet is drilling through the ejecta, just like a drill bit through the wall, it will spill sideways shocked material. Here you see it in yellow, known as a cocoon, which is engulfing the jet and co-evolves with the jet. And after the jet and the cocoon are escaping from the ejecta, the jet will power its own emission, the gamma ray burst, but the cocoon will also be able to emit its own emission. And this is actually a prediction that we published just a couple of months before this event. Okay, so now let's go over the observations in electromagnetic emission from this event. So let's recap. So far we have ejecta. The compact object will power a jet. The ejecta will power a kilonova. The jet will power a gamma ray burst. And then there is the cocoon that is formed by the jet interaction with the ejecta, and the cocoon will emit its own emission. Okay, so let's see. So we had gravitational wave detection. We didn't have to wait for long. Just 2 seconds after the gravitational wave were detected here on Earth, there was a detection of gamma rays. At first glance, this could have been the long-awaited confirmation of the connection between gamma ray bursts and binary neutron star mergers. But then a closer look, when we look at the energy of the gamma rays compared to the population of gamma ray bursts that we have detected before, we see that this event falls short orders of magnitude compared to the rest of the population, which is raising concerns whether this is actually a gamma ray burst. So there were two alternatives to how we can interpret this very faint event. The first is coming from the fact that we are not observing the jet while we're facing it, but we're actually slightly off axis. And this is a relativistic effect known as beaming. And the idea is the following. If we have a source that is emitting photons isotropically at its rest frame, okay, when we're actually boosting the source to the observer, so all the photons will be beamed to within the opening angle of the jet. So that means that an observer that will be facing the jet will get all the photons, but observer that is outside of the jet cone will miss all the photons. So if we're slightly off axis, it means that we will get some fraction of the photons. So this is one interpretation to why we get such a weak emission. Alternatively, what we have suggested is that the cocoon is the source of the emission, so we don't see the jet at all at early times. What we see is photons that are coming from the cocoon. So the cocoon is very hot because it was just shocked by the jet, and as the cocoon is evolving, it's cooling down, and at some point the cocoon will become optically thin, which means that photons can finally diffuse out of the cocoon and reach Earth, and these photons will be the source of the emission, which is called cocoon shock breakout. When the shock, the forward shock of the cocoon, the photons from this layer will be able to propagate to Earth. At this point, we could not have distinguished between these two scenarios, so we had to wait for future observations to tell us which one of these scenarios is the true, correct one. Okay, about 11 hours have passed, and then there was the long-awaited kilonova emission that confirmed the connection between kilonova that was argued few decades before this event and neutron star mergers. And what we have detected are two components of kilonova. So we saw this ejecta that I mentioned before and these quints, but initially the ejecta was very blue. What does it mean that it was very blue? It means that it was very hot, and the reason why it was very hot is the following. The neutron stars, you remember, initially we have some metastable neutron star before it collapses to the black hole. As long as we have a neutron star, the neutron star will power neutrino-driven winds, so neutrinos are emitted from the neutron stars, and these neutrinos will interact with the neutron-rich gas that is in the ejecta, and this will start producing protons, and these protons will change the composition of the ejecta such that the ejecta becomes less opaque, so photons can actually diffuse earlier from the ejecta, while the ejecta is still hot, which means that the emission will be relatively blue. So this is the origin of the blue component. As soon as the neutron star collapses to a black hole, there will be no longer neutrino-driven wind that will change the composition of the neutron-rich ejecta. And this neutron-rich ejecta, because we have neutrons, the neutrons can be captured by the atomic nuclei in the ejecta. And this rapid neutron capture by atomic nuclei before they undergo radioactive decay through beta processes will actually be able to keep the ejecta very opaque, and therefore the photons will only diffuse later time when the ejecta is already a little bit cooler, and therefore it will appear redder. In this event alone, for example, there have been 20 Earth mass of gold that were synthesized. This is our best shot of synthesizing heavy elements in the universe by this rapid capture of neutrons on atomic nuclei, and gold and platinum and other heavy elements were synthesized so efficiently. So this is the confirmation of the kilonova emission. And then, after we confirm the kilonova, we are still left with understanding what's going on here at the early times with the jet and the cocoon. Another 11 days, and we started to see a new signal. And this new signal came after about 10 days in different bands. So we had both X-ray and optical and radio. And where does this come from? So the jet and the cocoon are expanding in the interstellar medium, and they're shocking the interstellar medium, accelerating electrons, and these electrons will start powering synchrotron emission, which is known as the afterglow. So this is the part that happens after this bow shock is already sweeping material from the interstellar medium, and this is synchrotron emission. Now, what we could learn from this is the following. Normally, when we see the jet in front of us, we have seen many gamma ray bursts in front of us, we see that this afterglow emission is decaying consistently over time. The reason for this is that as it's sweeping material, the jet decelerates, right? Everything that is getting more massive must decelerate. And then as it's decelerating, the emission decays. In this case, not only did it not decay, it actually got brighter and brighter until about 100 days after the event. And this told us a very important thing, which is that the emission did not come from the jet. And the way that we can understand it is the following. Imagine we are here. You remember, because of beaming, we cannot see the jet. What we see is only the cocoon because of the beaming effect. Now, over time, the cocoon decelerates, which means that the Lorentz factor goes down, and this means that the opening angle of what we can actually see is widening. And the reason is that the angle that we can actually see is 1 over the Lorentz factor of the material. So as it's decelerating, we can see regions that are closer and closer to the jet. They have more energy, and therefore they rise in the afterglow. After about 100 days, we finally see the jet, because the jet has decelerated to Lorentz factor, which is equal to 1 over the angular distance between us and the jet. And this is the time where we see the jet, and after this, it starts decaying, just like what we would have seen if we would have been facing the jet from the very beginning. So this has confirmed that it is not an off-axis jet emission that we initially suspected. It's actually that the emission was all along dominated by the cocoon, at least until 100 days after the event. Okay, so we confirmed cocoon emission, and finally, the last observation, but definitely not the least, it's one of the most important ones, was that this event was so close by, only 40 megaparsec away, about 100 million light years away, that we could actually take a picture of this through VLBI or radio interferometry, in 2 epochs. The first is 75 days after the event, the second was 232 days after the event, where we can actually see the displacement of this source on the sky, and if you have 2 points at different times, you can measure velocity. So we could actually measure the velocity of the jet and found that the Lorentz factor of the jet was about 4, which has told us that we have a relativistic source, which is the jet, and this has confirmed the connection between GRB. Although we have missed the GRB, we know that there was a jet there, at least for aliens who were on the axis of the jet, they could have seen it, the cocoon emission and the kilonova ejecta. So this is the end of this event. But it told us much more than just this type of emission. Unfortunately, we did not have neutrinos, so only 2 messengers were detected, but this was good enough. And the lessons we could have taken from this event, just so you see how much physics was stored in this event, so many fundamental physics questions. We had 2 neutron stars forming a black hole. We could have learned about the equation of state of dense matter from this event, because this is tightly associated with the time it takes the metastable neutron star to collapse to a black hole. We can learn about black hole natal properties. What is the mass of the black hole when it forms? What is the spin of the black hole when it forms? The kick that the black hole receives when it forms. So a lot of black hole physics that we can do here. We can learn about the formation channels of compact objects in the universe. We can learn about heavy element nucleosynthesis, as we saw. Jet laboratory with observations across the entire electromagnetic spectrum, which I mentioned. And we can do high energy particles. We can place constraints from the null detection on neutrinos. And the last thing, which I haven't even mentioned, we can even do cosmology and constrain the universe expansion rate from this event. Because if we have gravitational waves, we can, from the gravitational wave emission, infer the distance, and from the electromagnetic emission, infer the Doppler factor, or the Doppler shift, which will tell us what is the velocity of the event. So if we have a velocity and we have distance, we can infer the Hubble constant, which tells us about the universe expansion rate. So all of this physics that is touching so many different parts in astrophysics was available to us in this event, and this is what makes them such events so important. Okay, so going back here, this is what we have studied. Unfortunately, it's been 8 years and we haven't detected any new event. What do we do now? We don't have any multi-messenger events to work with. So I would like to show you probably the most important events that we had since then. They are not multi-messenger, but nevertheless they're exciting, and there is a lot of physics we can do through them. So we have established that long gamma ray bursts are coming from collapse of massive stars. And short gamma ray bursts are now confirmed to come from mergers of neutron stars. So far, so good. We have 2 classes of gamma ray bursts, fully consistent with all observations we have had over a couple of decades. But in the past few years, in 2021 and 2023, there were 2 new events which at first glance are totally unremarkable and we wouldn't pay too much attention to them. These were 2 long gamma ray bursts, okay, not a big deal. Another 2 long gamma ray bursts out of hundreds. But the difference was that both of these events were followed not by a supernova emission, but by a kilonova emission, which we know is associated with short gamma ray bursts. And this has established a new class of gamma ray bursts in addition to the 2 that we already know. So instead of calling these long gamma ray bursts, let's call them collapsal gamma ray bursts after the collapse of a massive star. This will be short binary GRBs, and this will be the long binary GRBs, which is the new class. Now, the reason why this class is so interesting is because normally when we think about what is powering jet, and we will get to this in the next slide, we are saying we have a compact object, it's accreting mass from the disk, for example, and then it takes this mass and it converts it to outflows, and this is how we power jets. Now, here the time to accrete the entire star can be dozens of seconds, so no problem, we can power long gamma ray bursts. Here the time to accrete in a merger is a fraction of a second, so no problem, we have a short gamma ray burst. But how on earth can you take a disk in a merger, which accretes over a typical timescale of a fraction of a second, and power a long gamma ray burst that lasts for dozens of seconds? This is what was so puzzling, and this is why initially it was thought that it's not even coming from a merger. Maybe there is another source that can power a kilonova. So let's answer this question, and through this I will be able to walk you to the first question I started with. What is the central engine of the short gamma ray burst, a neutron star or a black hole? So now we have to dive a little bit deeper into the physics. So let me walk you through this too. So black hole, this is specifically for black hole jet launching. Okay, we have a black hole, it's launching a jet as it's accreting material from its vicinity. And if you want to know what is the energy of a jet, all you need to know are 3 quantities. One is what is the mass accretion rate, how much mass is accreted onto the black hole. This is how much accretion power is available for us. The second thing is the black hole spin efficiency. The faster the black hole spins, the more powerful the jet would be. The reason is that the jet is powered by twisting magnetic field lines that are coming from the disk. So the faster the black hole spins, the more energy is going into the magnetic field that is being twisted. Okay? And the third reason is that the third important factor is the magnetic field efficiency, which is telling us how much flux is available on the black hole. So once you know all these 3 quantities, which is just the product of these 3, then we know the jet power. So this is what we need to know if we want to understand how we can power long jets from mergers. Yeah?
What is the field efficiency of pure chronological parameter? How do you connect it to more ground physics? It seems like a pure chronological parameter.
Yes, I will define it here. If it's still not clear, please ask me again in the slide. So we have this connection. Now, in mergers, we are very lucky because there is a lot of angular momentum. We don't have to worry about the spin. The spin is always roughly 1, so this reduces 1 degree of freedom that we have. And then we're left with just this relation between the jet power, the mass accretion rate, and the magnetic field efficiency. Let's start with the mass accretion rate. The mass accretion rate can be solved analytically. I will not derive it here, but we can talk about this more later. And what you find is that it goes as t to the minus 2. Importantly, we see this in all numerical simulations. So this is fully consistent with what we find numerically. The other thing we can find is that the jet power is remaining constant, but this is coming from the fact that the flux on the black hole is constant, and this is due to the fact that the post-merger disk is very compact, so the magnetic flux is advected onto the black hole within a very short time, and then it just remains there. So the total flux, which scales with the jet power, remains constant. And then when we think about the magnetic flux efficiency, it's defined as the total flux, or the jet power, it's the same, over the mass accretion rate. So this is the definition of the magnetic field efficiency, and we can actually calculate it, and you find that it must scale inversely with the mass accretion rate, and this means t squared. Now, even if you haven't followed this part, we can look at how it evolves over time. So the mass accretion rate goes down as t to the minus 2. And then the magnetic field efficiency goes up as t squared. But it cannot go up forever because it's efficiency, right? Efficiency must saturate at about 100%. And once it saturates, it does not obviously change anymore. What happens at this point? Why does it saturate here? This is where the black hole is saturated with magnetic flux. It cannot accept more flux. Okay, this is called magnetically arrested disk. And this is the time that the jet power, which is the product of these two, will start going down. And you can see it here. Okay, so we actually assume this in a sense, that the magnetic flux is advected onto the black hole within a very short time and just remains there. So this is basically the same as this, and then it will start going down. But the important lesson from all of this is that the time of the jet is set by the med time. So if we know the med time, we know the time of the GRB, and this is what we're here for. We want to understand how to produce long GRBs from mergers. So if we know the med time, we know how we can produce long GRB. For example, if we were to start with higher flux, the med time will commence earlier, and the GRB will be shorter but brighter. Okay, so this is the exercise, and then we can go to numerical relativity simulations, and what we find is the following. So this is a suite of about 20 different simulations of black hole neutron star mergers and binary neutron star mergers, and the gray lines are the numerical data, and the thick lines are log average of the numerical data, and we can divide it into two groups. The first group, which is the upper curve, is the massive disks, about 0.1 solar mass. The lower curve is the less massive disks, which are less than 0.01 solar mass. So this is the mass accretion rate. This is the right vertical axis, and this is what we see here. Now, if we would have maintained 100% efficiency, the jet power will just be m dot c squared, so it will just coincide with the mass accretion rate. But we saw before that it will start initially flat until it gets med, and only at the med time, I remind you that the med time is only when the efficiency is 100%. Yeah, right here. So this is the saturation level. So only the med time, the two will coincide. So initially it's flat and then it goes down. So we can play the following game. If we start with very high flux, we have too much power compared to the observed population of short gamma ray bursts and long gamma ray bursts, and therefore this can be ruled out observationally. If we start with less flux, then what we would find is that, that if you have a less massive disk, you can actually fit both the time of the jet and the power of the jet. So this is consistent with the short GRB population. And if we have even less flux, and we are in the regime of a massive disk, this will intersect with the long GRB population, and this will be the way that we can produce these long GRBs.
Excuse me, what kind of equation do you use to calculate all these things?
To calculate what?
What kind of equation you use
Yeah?
to calculate this effect?
What effect?
You explain something.
Yes.
What kind of equation you solve?
So here there is no equation. You're asking how I generate this curve?
How you generate?
This is from a numerical simulation, fully numerical relativity simulation that is involving GR-MHD equations. And what you're finding here is what is the mass accretion rate on the black hole as a function of time from the simulation. And then I compare this with the observed population of long and short GRBs. Does this answer your question? Yes. Okay. So what we see here is that not only do the massive disks can actually produce the long GRBs, they must produce the long GRB because they do not intersect with the short GRB population at all. So either they would power a very bright short GRB, but we don't see those observationally, or they power a long GRB, which is exactly what we want. So this is a very strong result that is connecting the mass of the disk with the GRB class. And this opens a very important channel for us to study binary configurations of mergers. Because if we can connect the mass of the disk with the GRB class, we can do the following. This diagram shows the total mass of the binary. This is the mass ratio of the binary. We know from simulations that very massive binaries that are with a high unequal mass ratio will form a massive disk. But I just showed you that massive disks, is it time already?
No,
okay.
To ask questions.
Oh, sorry.
Okay, later.
So we know that very massive disks power long GRBs. So for the first time, we can connect different configurations of mergers. What is the mass and the mass ratio of the merger with the class of the GRB? Now, what about the short GRB? How do we power them? So we have two options. One, and this goes back to the question I started with, the first slide. They can be powered by black holes with less massive disk, as we just saw here. Right? So we saw here that these less massive disks can power the short GRB. So this is one option. And they will be powered by these low massive disks by equal mass binaries. Alternatively, a neutron star can also power these short GRBs, because I remind you that these neutron stars can last for a fraction of a second before they collapse to a black hole. Maybe the neutron star during this time can power these short GRBs, which also last a fraction of a second, and neutron stars will normally emerge for this roughly lifetime for less massive binary mergers, so they don't promptly collapse to a black hole, but they have some phase of a metastable neutron star, and they can power a short GRB. I also remind you that neutron stars will have neutrino-driven winds that will replenish the disk, and therefore neutron stars are coming with high mass disks. So we have two candidates for the origin of the brightest events in the universe, these short GRBs. One is black holes with less massive disks, and one is neutron stars with high massive disks. How can we tell the two apart? Is there a way to do that? As you remember, as far as the jet is concerned, there is no difference between black holes and neutron stars. So how do we do that? Let's recall that there is another electromagnetic counterpart, kilonova, which, unlike the jet, cares a lot about whether it's a neutron star or a black hole, as we've just seen in GW70817. So this is the story. We predicted that black hole with massive disks will power the long GRB. And here are the two candidates, black hole with less massive disk or neutron star with massive disk for the short GRB. We can use the kilonova to infer the engine of the GRB in the following way. Kilonovae have at least two properties we can use. The first is the brightness of the kilonova. So the kilonova, I remind you, is powered by this ejecta from the merger. Most of this ejecta is coming from winds from the disk. So we have a connection between the disk mass and the kilonova brightness, but we also have a connection between the disk mass and the GRB. So we can use this. So for example, long GRB will come with a massive disk and therefore should have a bright kilonova. So Now, if the black hole with less massive disk is the origin of the short GRB, it will have a faint kilonova. And if it's a neutron star with a massive disk, it will have a bright kilonova. So one prediction is if we see bright kilonova with short GRBs, it's a neutron star. If it's faint kilonova, it's a black hole. Now we can even make the problem over constrained by introducing another dependency, which is the color of the kilonova. As you remember, if we have a black hole, the kilonova will be relatively red. So we expect a red kilonova. If it's a neutron star, we expect the kilonova to be relatively blue, because the photons are diffusing at earlier times when the kilonova is still hot. So we just need to measure the kilonova with the short GRBs, and we know the engine of the short GRB. So what does the data tell us? I should warn you, the data is still very much uncertain. So here you should think about this more as of a framework. Once we have more observations, we can actually study this. But we already have some data and some fitting, which may or may not be true. But this is the following. These are the long GRBs. These are the short GRBs. This is the GRB time scale, and this is the ejecta mass. Now, these are the kilonovae. And the pie charts are demonstrating the relative contribution of the different components, the red, purple, and blue components to the ejecta. What you see is that all long GRBs are associated with consistently redder kilonovae, which are also very massive. The mass of the ejecta is more than 0.1 solar mass. So this confirms our prediction that the long GRB, the new puzzling class of GRBs, are coming from massive disks around black holes. So this is good. As for the short binary GRBs, their kilonovae are much less clear because the data is poorer. But if we are forcing some analysis on the short binary GRBs, what we find is that all their kilonovae are consistently bluer, and they're comparably bright. There is a factor of 2 or 3 between the brightness, but this is negligible compared to orders of magnitude dynamical scale of the ejecta. And this confirms that these are coming from neutron stars with massive disks. Okay? So this is how we can potentially establish the origin of gamma ray bursts and their central engine of gamma ray bursts and connect it with binary populations. So I think it's a big step forward. And what you see here is M1 and M2, which are the masses of the merger, and how you map each merger to GRB class, remnant, kilonova class, and so forth. So this is just the first attempt. We still don't have all the data we would like to have, but this framework is highly promising, and with this framework we can actually constrain the equation of mass of neutron stars, because this tells us if we have the observational ratio between long and short GRBs, we can know where to draw the line here between long and short GRBs, and this will constrain the equation of mass of neutron stars. I'm running much slower than I expected, so I will stop here, and I'm happy to talk more about maybe future of multi-messenger astrophysics after the talk individually. Thank you very much for your attention.
Thank you. Yeah, so now I have 2 microphones. I would like to ask someone to help me to take care of this one, because it's a bit difficult, and you serve this part of the audience, and I will this.
Okay, thank you very much for the talk. It was quite a nearly popular science level, but it's good because it's very varied audience, although I think we're all physicists, so we can really trying to go back to physics. So I had a few questions that came to me when you were discussing, even though the presentation was excellent, so maybe I'll focus on one. I think I never kind of understood what's fundamental about this 2-second the time division between short and long gamma ray bursts, because I'm cosmologist. So naively speaking, I think I can imagine that there could be, because of variance in masses, orbital parameters, there could be actually outliers that would, creep a little bit into the one of the two binary separation, but yet you insist to have this split and very firm 2-second, looks a bit arbitrary threshold. So could you maybe explain a little bit more about that?
Yes, I fully agree with you that it's very arbitrary. It's actually an observational feature. It's not something that has any theoretical fundamental physics behind it. what I would say is that we don't need to stick to this 2 second necessarily, because you see that at least in this sample, all the short GRBs are shorter than 1 second, and all the long GRBs are longer than maybe, depending on how you define the time, but roughly than 20 seconds. So there is a big gap between them, and by no means 2 seconds have any significance. So yes, I think it's important to make this clear, but I think it's also clear that there are two populations that are rather distinct by observations.
Right, thanks for sharing this for me. Can I have a second question? That one I actually wanted to ask during the talk. So indeed, it looks like a quite powerful prediction for you if you split the magnetic initial, flux, and you can predict this, long and short powers and the fading of the jet. But do we have any, reason why this starting efficiency should come in this to nearly B-model distribution, or can you expect there could be completely full spectrum of starting magnetic flux efficiency, and therefore you could have some transition between these two predictions?
You mean that the initial magnetic flux it should be continuous. I do agree with you. Okay. One important question is how this translates to. Okay, so I should say this. There are two scenarios. If you start with less flux, you can either get a longer GRB, which would be basically, just following this line, or you can get a fainter GRB, and this would depend on how the flux scales with the disk mass. Now, what we find in simulations, if you can trust this, is that actually the dimensionless flux is constant across disk masses. So what remains constant between mergers is not the total flux, but the dimensionless flux, which tells you that the met time will always be the same time if you have a black hole remnant, and you will also have a long GRB, which means that if you have less flux, you have a fainter GRB rather than a shorter GRB. And therefore, this is another evidence for us to why the short GRBs must be powered by a neutron star.
It's very nice. Thank you very much.
Here, yes.
Thank you very much. I have an observational question. You said that the derived gamma Lorentz, the Lorentz factor of the gravitational wave event was 4?
Yes.
That's the after, or after the breakout, or the prompt one?
This is
because I thought GRBs had a stronger gamma.
You're right. The Lorentz factor of 4 is the average of the Lorentz factor between day 75 and day 232, which is the VLBI observations. Okay. This is well after the jet is already decelerated. Okay, yeah, so it started probably much higher than this.
Yeah. Thank you.
Bożena?
You didn't talk much about gamma ray spectra. But when you discuss the difference between jet emission and cocoon emission, I would expect that the spectrum should be different in those cases.
Yes.
Am I right? So that's additional.
It depends what you're asking. I agree with you. Some people would argue, so what we saw in GW17 is a very clear hard to solve evolution in the spectrum in the gamma ray burst. This is a prediction of the cocoon shock breakout emission. But the people who are advocating for the jet emission, or at least were advocating for the jet emission, argue that you can also have hard to solve evolution in the spectrum for off-axis jet emission, which is different than the normal GRB emission. So I don't know if everyone would agree that you expected a different spectrum. I do agree, but I should also say that this is not a consensus.
Yes, here.
So, now that you are in this slide, something that I wanted to ask.
Yeah.
So, in this model for the jet power evolution, it seems that the magnetic efficiency always rises up until you get to the mat state. Mm-hmm. Are there theoretical reasons to believe that this will always be the case, so that all these accretion flows will turn matte, or one is sufficient to expect that it will reach a maximum and stay there? And if there is a theoretical reason to think that they all will become matte, what is this reason?
So Okay, I can say phenomenologically, all numerical relativity simulations of merger ever conducted, they find a constant rise in the magnetic field efficiency. Most of them don't get to the med state because it's much farther and much longer than what they can actually simulate. On a theoretical ground, I would say the following: the MAD is set by this quantity. This quantity scales inversely with mass accretion rate. Mass accretion rate is almost always found to be t to the minus 2. So as long as this goes down, and the flux at least does not go down, the flux, okay, so you are not going to lose flux before you're reaching a med state, because only this you start reconnecting the magnetic field. In the meantime, you are losing a lot of mass. So the mass accretion rate goes down as t to the minus 2, which means that eta phi must go up. I just don't see any way that the mass accretion rate goes down and the flux will go down before reaching med, because you're only accreting more and more flux from the disk. So I don't see any way that it will not reach med.
Right. Well, that is true, but also when you so when you reach the mat state and the magnetic flux stops the accretion flow,
yeah.
The fact that you cannot feed the black hole with more matter also means that less magnetic flux will be transported to the black hole, and what we see in simulations is that all the magnetic flux will drop again. So
yeah. This is the reason why the jet power starts falling down, because you start reconnecting magnetic field. So the magnetic field will start following, will start going down, but the efficiency will be the same because it's the ratio between magnetic flux and mass accretion rate.
I see. So the mat state will not necessarily be sustained forever, but it will stay there for some long time.
Yeah, I might have some backup slides. That's not.
But I think I understand.
Okay, so maybe you can discuss this later in more detail.
Yeah, so you can see it here. This is actually numerical data. You can see that this is eta. This is the dimensionless flux until it gets met, and then it remains there. And this is the jet power. So you see it's constant, and then as it's approaching med, then it starts falling down.
I see. Thank you very much.
Mm-hmm. Other questions? Do we have questions from the Zoom audience? If yes, then just please turn on your microphone and speak up.
Hi, I have a question about...
Anjita, okay, please.
Yes, thanks.
Zoom.
Is there any effect of a gravitational lensing by foreground galaxies or galaxy clusters affect the observed GRB?
Anjita, we cannot hear you. Okay, I read the question. Gravitational lensing by galaxies on observed flux intensity. The question is about gravitational lensing on GRB observed flux intensity. Can you comment on that, Ore?
If I understand the question, is if there are any gravitational lensing effects on the GRB flux and whether this is something we account for. I think there might be some gravitational wave lensing events, but I would think that they're probably very rare. So I think this is complicating things for probably small samples that we're working with. But when we think about large samples, then I don't think that correcting for individual effects should be a major concern for us.
Okay. There is one more question in the back.
Yeah, thank you for this nice talk. I have one basic question that you have told the flux actually varies as t squared and mass accretion rate varies at t minus 2. So my question is, what kind of physical mechanisms or initial conditions actually dictate this kind of behavior?
Okay, it's too much. So there are two components there. Actually, I can do it by hand. So you're asking about this equation?
Yes, but yes, why it is varying like that with time? What is the physical motivations or physical mechanisms behind this?
Right. So the mass of the disk scales as t to the minus third, and this is something that I can show you later, like the derivation of this. This is a self-similar solution for the evolution of disk mass. And then this divided by t will give you t to the minus 4/3. And this this component will give you t to the minus 2/3, and it's coming from the fact that the disk is viscously spreading over time. So it means that not all the flux on one side, on the disk radius, will actually reach the horizon, which is this part. So this type of expansion of the disk will give you t to the minus 2/3. It just reduces the mass accretion rate that is reaching the horizon. And I can also walk with you through this derivation. Is this answering your question? Yeah.
Okay.
Yes, I think we can stop at this moment, but of course, if you are interested in more details and would like to talk with Ore, we have a blackboard upstairs, and everything that you want to ask will be, I think, more clarified if you want to join the discussion, because we have to finish now. Let's thank Ore. Thank you.